see. So let's start with grabbing the equations that are correct, which is to say, I should probably put on a mouse here. Make life easier. Can you see okay?
Yeah.
So
Say like 1654 or something.
yeah, that's appropriate. Alright, fine. Let's start with this. The goal is to try to solve this, right?
Yeah.
Is to solve this. Now what we're going to do is first we're going to put it in step 1, put it in state equation form. Put it in state equation form, right? We have we say Vc is equal to we define x1 of t to be Vc of t, right?
Yeah.
Define and also define x2 of t equals, as you might have seen yesterday, dvc by dt, dvc by dt of t. Okay, that means and I'll give this a number here. Okay, this is equation 1. Okay. These two together we can call them equation 2. So with that, equation 1 becomes so using 2, 1 becomes, let's see, what does it become? LC dx2 by dt plus RC x2 plus x1 equals 0, right? That's number 3. Okay, so and then 3 together, well, let's let's make this 2.1 and 2.2, 2.1 and 2.2, and these two together will be referred to as 2. So putting let me see, 2.2 and 3 together, we get, what was 2.2? dvc by dt, dx2, sorry, dx1 by dt, because this is equal to dx1 by dt, right? Yeah. Recall that vc was equal to x1,
Right.
so dvc by dt is dx1 by dt,
Right.
right? So then we get dx1 by dt equals x2, right? Which we can call again 4.1 just for convenience. And the second equation is, what was it? Is this equation over here? dx2 by dt equals minus 1 over LC times all the rest of it, x1 plus RC x2. Be sure it's RC x2, right? Yeah, we did.
Right, you
work
get
that way.
minus 1 over LC.
Yeah, I put this minus 1 over LC here. Correct?
Oh, you subtracted it over.
Yeah, I move it onto the other side, I get the minus,
Okay.
and then I move the 1 over LC over here.
That's good.
Okay? Right, and these two together we can call 4. So fine, 4 can be expressed in matrix vector form. Matrix vector form. First we have to make a couple of definitions. I'll move this up a little bit. So first we define the vector x of t to be x1 of t, x2 of t, and that's equation 5.
Sorry.
And then we get, let's see, d by dt of x1, we'll write it in long form first. x1, x2 equals Alright, now we have to be a little careful just to make sure there's no mistake. Put the x1 over here and the x2 out there. Put it as a function of time right here. And we have the first one is 0 here, 1 there. I think we had got this far yesterday, right? Maybe. Minus 1 over LC here, and RC over minus 1 over LC, that is minus R over L, right? Am I right?
Yeah, dx1 dt is equal to x2, so that's right.
That part is right. What about the other two?
Dx
Yeah, why don't you just put them in yourself, and then we can check against mine.
LC, and negative R over L.
R over L. Okay, then that I think is probably correct.
Yeah.
Okay. So this is basically our state. Our state equation doesn't have any inputs. And so let me just label that. Okay, these are the state equations. State equations with no inputs. No inputs. That's also fine. I should have probably mentioned that in class, that you can actually have a state equation with just a state and no inputs.
That's kind of what we've been doing for like the last all the circuits we've done.
Less interesting than otherwise, but yeah. Okay, so now we will switch gears and we'll move to the solution stage. Okay, so now let's see, what did we call that? Number 1. Okay, number 2, solve, and what was the name of that? So solve 6, which we may as well just copy here for convenience. Okay, it's still legible, so that's fine. All right, now let's write it. I'll write 2 over here. 2.1 and aside eigen decomposition of an arbitrary 2x2 matrix. 2x2 matrix, right? Yeah. So say A is equal to small a, small b, small c, small d, in general. Right? And let's call it the eigenequation. So we do not yet know why we are doing this. We are just doing this. Okay. Eigenequation is basically A times, I think we agreed to call them P. Okay, A times P. P is an eigenvector, is lambda times P, right? And this is the same thing as A minus lambda I times P equals 0. 0 is a vector 0. Right, which is the same thing as, so then let me write it down. To allow, let me actually give that a number. That was 6, so this should be 7, and this should be 8. To allow 8 to have non-trivial basically means non-zero, not equal to 0. Okay, non-trivial solutions for P. For P, A minus lambda I must be rank deficient. So how are your concepts of ranks of matrices?
Just, well, I know that rank is the number of linearly independent.
Yeah. So you know what linearly independent is, right?
Yeah.
Whatever.
It's just that
I have a matrix and I have columns.
Yeah,
I have 10 columns.
That means one of the vectors can be expressed as a linear, as like a combination of the other vectors.
So basically, some addition or subtraction with weights of the others.
Weights.
Or another way to think of it is you can take all of them and you can put weights on them. Okay, any weights, positive or negative.
And the only weights that can make them equal 0 is 0.
Is 0. Yeah. That's right. That's linearly independent.
Yes.
Okay. And if you can find weights that are non-zero, then it's linearly dependent.
Yeah.
Okay, that's the same thing. Great. So if a matrix has linearly dependent columns, then it's called rank deficient.
Yeah.
You can reduce it down to well, let's not get into that. Okay, and if it is rank deficient and if the matrix is square, okay, this is also square.
Yeah.
Okay. You can have, then the determinant is 0. Implies determinant of A minus lambda I equals 0, right? And that's 9. Okay. So far so good. Okay. So now let me give you sort of a preview of how we are going to go about using this. All right. Before we actually do it, you're going to write out an equation for the the equation for the determinant, which in this case is relatively easy. Okay. And that will turn out to be so the P is no longer involved in this equation. Okay, that will turn out to be a polynomial in terms of this lambda, and that polynomial is called it has a special name. It's called the characteristic polynomial.
Yeah.
Okay. Then we solve that since we solve that for values of lambda that do actually make the determinant 0, and since it's going to be a quadratic, we're going to get 2 values. All right. Having got them, then we are going to return to this 8 equation, right? And then we are going to try to see whether we can use our values of lambda for which. So we know already from theoretical considerations that if I put any lambda apart from those 2 lambdas over here, p has to be 0. Because you get that, right?
Yeah.
Because those are the only 2 lambdas for which a minus lambda I is singular.
Yeah.
And if it's not singular, then p has to be 0. Because you can invert the whole thing and put it over there, and you're going to get it to be 0, right?
Yeah.
So what we are going to do is we're going to try to get an expression for p when you put that particular lambda in there.
Right.
And then you'll find that this is basically 2 equations, right? A minus lambda I times p1 p2 equals 0. You'll find that because lambda is specifically chosen to make this this matrix, not quite that matrix, but this matrix singular.
Yeah.
That means that the 2 rows are linearly dependent, which means that the second row is just a multiplication of the first row by some constant number.
Right.
Okay.
That's what singular means.
Well, yeah, but that's in this particular case.
Okay.
That's what linearly dependent means.
Well, yeah, but what does singular?
Oh, singular means the same thing as the fact that its determinant is 0.
Oh, okay.
Yeah. Okay, I should probably write that.
Yeah.
Okay. Singular. Okay. Means 9. Just if you say a matrix is singular, so it should be a square matrix, and it's basically its determinant is 0 / it's it's not invertible / whatever.
Yeah.
Okay. All of the above. Okay. So that's quite useful. So basically, these two equations are going to become the same.
Yeah.
So we are going to find that p is not uniquely determined, but if you pick one member of p, then the other one is.
Okay.
And the other one is going to be dependent on the particular lambda that you put in, and there are 2 values of lambda, so you'll get 2 different p's. That's what we are going to get.
Okay.
One associated with each lambda. Okay. So maybe this will become clearer as we go along, but please, if it is not clear, just stop me and ask, because this is almost the crux of eigendecomposition.
Yeah.
Okay. All right. So now what we're going to do is determine. So a minus determinant a minus lambda I. Let's scroll it down a little bit. Equals determinant of we'll just write down. It's supposed to be parentheses. So a was just a b c d over there. So a minus lambda is going to be a minus small a minus lambda, b c small d minus lambda. Right?
Yeah.
And that we know there is the formula. It's basically the product of the diagonal terms minus the product of the off-diagonal terms. So a minus lambda times d minus lambda minus b times c. Okay. And that we can now write down equals so it's lambda squared minus something times lambda, and that something is probably a plus d. Yeah, I think so. Yeah. Minus
a plus d.
Yeah. Minus let me see, plus AD minus BC.
Right.
Okay. AD minus BC happens to be the determinant of the original
Matrix.
Of the original matrix, right? Equals 0. Determinant of the original matrix. Not that this has any tremendous significance for what we are doing. Still, it's nice to know. Okay, so look, okay, let's give this a number. 10, 11. Okay, now we want to the solutions of 10. The solution of 10 is, what is it? It's lambda 1 comma 2 equals minus this, which is plus a plus d. Okay, is this right? No mistake so far, right? I don't think so. Yeah. Okay, plus a plus d plus minus square root of a plus d, the whole thing squared, minus 4 times that determinant AD minus BC, and the whole thing divided by 2. Right?
Yeah. No, but I mean, if it's late at night, what I can do,
And that's 12 here.
I pick you up in the, so how much?
Okay, not 10, actually 11 here. Right? Okay, so we'll keep this in mind. Right?
10 and 11 are the same.
Yeah, 10 and 11, well, they are, yeah, but here you can see it nicely. Okay, so now, so these are the lambdas. Now we want to, yeah, so we have found the lambdas. We have found the lambdas. So now next we want to find P, right, using again 8. Okay.
8 is just the eigenequation.
8 is just the eigenequation. Yes. Okay. Okay. So now we'll just move this to another page. Okay, so that's what we want to do. So 8, which is a minus lambda I times p is equal to 0, right?
Yeah.
So let's write the whole thing out in extreme detail. Okay, so it's going to be a minus lambda, b, c, and d minus lambda. That's a minus lambda I. And then P is going to be my P1 and P2, and the 0 is going to be 0, 0, right?
Yeah.
So what should the equation number be? 13. Right? So I'll make those comments, or at least some of those comments that I made. We know that if lambda is not equal to lambda 1 or lambda 2, okay, the only solution possible is P1 comma P2 equals 0, okay, because okay, that's a minus lambda I is P 0, because a minus lambda I is non-singular, right? So we know that. So this gives us some motivation to try just that lambda 1 and that lambda 2. Okay. So keep in mind that we will try. We are interested only in lambda equals lambda 1 or lambda 2.
Yeah, just a quick question.
Yeah.
Isn't a minus lambda singular?
Sorry?
Isn't it actually singular?
Isn't this
A minus lambda I.
the only is p1 equals no, if because it's if
not
lambda is
equal
not
to-
equal to these two.
Yeah,
Okay.
if
That-
it is,
that-
then
yeah.
it's
If it is, then it's singular.
Yeah.
So that's the case that we are interested in.
Okay.
Okay. All right. So that's what we are going to do. So then what we are going to do? Let's say, so let's try lambda 1 first. Try lambda equals lambda 1 first. I'm not even going to actually use the expression because it's just messy and we don't need it. Okay. We might need them later, but not right now. Okay. Then we have. I'll just copy this over. So lambda 1. Oh, wait a moment. What did I do here? It should have been b. So not lambda. Okay, up here it should have been b. Lambda 1. Okay, equals 0, and okay, fine. And I will call these now. So this is going to be, I'm going to call this now P1, okay, and I'm going to call this P11 and P12. Okay, so P1 is going to be the first. That one corresponds to lambda 1.
It's the first eigenvector.
Yeah, it's the first eigenvector. Okay. So then I just write out the equations, and what we are going to show painfully and laboriously is that the two equations are going to be the same. All right, that's the part that's actually a little bit painful, but we'll do it once.
Yeah.
Okay. So it's going to be a minus lambda 1 p11 plus b p12 equals 0, and let's give these numbers. 14. And the other one is going to be C times P11 plus D minus lambda 1 times P12 equals 0.
Right.
Okay, that's what it's going to be. So let's let's call this 15.1 and 15.2. Let's deal with 15.1 first, and then we'll deal with 15.2, and we'll see that we get exactly the same solution as for 15.1. As we should, because it should be the same equation, although it's not apparent by looking at it right now.
Yeah.
Okay. Okay, so solve. So use 15.1 to write. Which one is going to be easier? Let's see, to write P12 in terms of P11. All right, let's just say we do that. Okay, so yeah, that's what we're going to do first. Then we are going to do the same thing with 15.2, and we'll find that it's exactly the same equation.
Okay.
Right? Yeah. And that will require some hassle. Okay, so let's see. How does one write P12 in terms of, so P12? We get P12 equals minus A minus lambda 1 times P1 divided by B, right? We'll call that 16.
Yeah.
Is that what you get?
Yeah.
Yeah. Minus A minus lambda 1 times P1 over B.
Yeah.
Okay. Now we do the same thing with the other one. Now use 15.2 to express P12 in terms of P1. P11. So if I do that, then what do I get? So actually, instead of dividing by B, because we don't know whether B is 0 or not, right? Okay, I will just write that as OR. Can we divide by A minus lambda 1? Will that always be non-zero? Where's lambda 1? So it's A plus D plus blah blah blah. So suppose D, everything is 0 except for A, right?
There's no way.
So then what we get is A square minus 4A.
If
everything is 0, then we just get A square over here.
Yeah,
then this becomes just plus minus A.
One of the solutions would be 0.
One of the solutions is 0 and the other solution is A.
Right.
And A minus lambda 1 and A minus lambda 1 will also be 0 because lambda 1 of the solutions. So A minus lambda 1 or A minus lambda 2, we have to get to the lambda 2 case later. Alright, so okay, so this is not the greatest way of doing it. Okay, but we'll just do it anyway, right? Pretending that B is not 0, just for a little bit of insight. Essentially, we want to show that these two equations are linearly dependent, which we knew because it's basically the same thing as this, right? So let's just go ahead and do this, and then we'll see it just in another way. Okay. So then what happens is that for this one we're expecting then P12 equals minus C times P11 divided by D minus lambda 1, right? And that's 17. Okay. Now the claim see, if these two things were somewhat different equations, then you could have got different answers for some unique answer for it. So now the claim minus A minus lambda 1. Okay, let me first make the broader claim. 16 and 17 are exactly the same equation. Now the proof of the claim need to show that minus A minus lambda 1, basically the coefficients, okay, equals minus C over, there should have been 1 D minus lambda 1, right?
Yeah.
Okay, and then if I just multiply it out, I'll get my characteristic equation back. That's what's going to happen, right? Or I'll just move everything, all the numerators, all the denominators up, or minus A minus lambda 1 times D minus lambda 1 equals minus BC.
Right.
Okay, and so then we can cancel out the minuses, or minus lambda 1 plus lambda 1 squared plus lambda 1 squared minus lambda 1 a plus d, right? Plus ad minus bc equals 0, which is exactly the same equation, and lambda 1 is a solution of that. Okay, which is exactly what was the number of the previous thing? Exactly 11, which is exactly 11, of which lambda 1 is a solution, right? Okay. So this is telling us that there is nothing you know, if you do this one or that one, it's the same thing.
Yeah,
that's what it's telling us. Okay, and it can help assuage some lingering discomfort with what we are about to do next, which is we are going to say that the best information that we can get is that P11 and P12 are related, but by either this or that, it's going to be the same thing. Okay, so I'm just going to choose P11 to be 1, and then P12 to be will be given by whatever this is.
Yeah.
Okay, or I can actually, the best thing I can do, if I move this B up over here, I want to choose something that doesn't involve divisions and so on. So suppose I choose, oh yeah, I think I know what to do. Suppose I choose P12 to be this, okay, and P11 to be B.
P11 to be B. Okay,
yeah. Because I just choose P11 to cancel out the B, and P12 to cancel out this, if I move this on to the other side. So then it looks nice. I don't have any divisions and stuff like that.
Right.
Because it doesn't matter what you choose so long as not 0. 0 will give you the trivial solution. But you can choose anything you like, and you can try to make it such that there are no divisions involved. Okay.
Yeah.
That's what we are going to do. What this let me just write down what I just told you. What this means is that we can use either, what was that number there, 16 or 17, yeah, or 15.1, and yeah, let's write 15.1 or 15.2, okay, to solve for P11 and P12. There will be no difference. It makes no difference which one we use. No difference which one we use, right? And so let's just use 15.1. 15.1 is that. Equal 0, which we can give another number. Do we have any numbers? This should, no, this is not really an equation here. 18. Okay. So now here comes a real thing that one needs to appreciate, because this, well, the above reasoning tells us that we can choose one of P11 or P12 arbitrarily, right? And the other one gets determined. One gets determined by 18. Right, that's what it tells us. Okay.
Right.
And now it's all comes together because that equation system was singular. If it's singular, then it doesn't have a unique solution. If it not, then this is exactly what it means not to have a unique solution. I can choose one number for one of them, the other one will change.
Yeah.
So it has actually an infinity of solutions.
Yeah, because there's many eigenvectors for that one.
Well, no. Yeah, there are many eigenvectors. Well, so the eigenvectors are usually So the eigenvectors are usually taken to be within some scale. Okay. So if I take P to be an eigenvector, then any alpha times P is also an eigenvector.
Right.
Yeah? So that doesn't really matter. So it really matters the direction in which it is pointing. Or you can normalize the eigenvector to size 1. You can make the norm 1. Then it's going to be unique.
Yeah.
Okay. Actually, even then it's not unique because you can take minus of the eigenvector and then it's at least 2.
Yeah.
So that's how it is. Excuse me a second.
That's pretty good.
Okay, so fine. So a convenient choice. Avoiding division by anything. Okay. Have I got this right? Yeah. Okay. So make P11 equals B. P12 implies no, not actually. It's lambda 1 minus A. I think actually this is minus. Implies P12. Let's just make absolutely sure of it. Yeah, I think it is lambda 1 minus A. Right, because then the 2 cancel out. Right?
Yeah.
Okay. So this is like an important thing. So okay. So now hence we have P1 equals whatever they are, B and lambda 1 minus A. Okay, that's 20. Now let's see, we have to go back to this. Let's try lambda equals lambda 1 first. So now let's now we try lambda equals lambda 2. Okay, the whole process is completely identical. Okay, completely identical to the above. Just replace lambda 1 by lambda 2, right? Lambda 1 by lambda 2 and P11 P12 by P21 and P22. P1 by P2. Yeah, that's basically all there is to it. Okay, so we get exactly identically P2 equals same B, okay, and lambda 2 minus A. Right. 21. Okay, how long has all that taken? Oh, almost an hour. Okay, never mind. So worth going through it once. Do you have to go at any point? No. All right. So now we've done this eigen decomposition. Therefore, we have P equals P1 and P2, right? Which equals whatever those things are. It's actually BB, which is as this pretty much the same thing as 1 1 actually.
Mm-hmm.
Okay, BB lambda 1 minus A, lambda 2 minus A. Let me just deal with this. Right, so that's P.
Yeah.
So A is A equals P lambda. Did we define lambda?
No. It's just lambda 1, lambda 2. We haven't defined
Okay, we can define it here. There's some space. Okay. Define lambda equals lambda 1, lambda 2, 0, 0. And that can be 12.5. So it's going to be P lambda P inverse.
Right.
For completeness, we are also going to compute P inverse. All right. All right. So this is 22. Okay, we are where T is given by 22, lambda, capital lambda, is given by 12.5. Okay.
Yeah.
And now let's compute. Let's also write out P inverse. Okay, so
It's a 2 by 2 formula. Right?
yeah, the 2 by 2 formula, which I think I actually remember.
I wrote it out, so maybe we can see.
Okay, yeah. Well, let me write it out, and then we can compare.
Yeah.
It's a good way of making sure that nothing is wrong. Inverse equals okay, lambda 2 minus A B minus B A minus lambda 1, and then there's a determinant. What is the determinant? B times lambda 2 minus A minus B times lambda 1 minus A, which is equal to times so everything cancels, so it's actually just B times lambda 2 minus lambda 1.
Yep.
Correct?
Yeah, that's what I got.
Is this right?
Yep.
Exactly right?
Yeah.
Does it exactly match?
Yes.
Okay, good. So P inverse equals that, right? And we can give it a number 23, and then we can also and P inverse is given by 23 below, right? It's 22.5 here. Okay, so here we have it. So let's write out the whole thing in gory detail now. Okay, because this is something we will. This is a 2x2 general formula. Life is going to be really good from now on. Okay, because we just use this general formula and never go through this derivation ever again.
Sounds good.
Yeah. So so what we've just shown. To summarize, let us say. Summarize, A, B, C, D equals what was P now?
B
B lambda 1 minus A.
Lambda 2 minus A.
B lambda 1 minus A, lambda 2 minus A, then lambda 1, lambda 2, and then it was lambda 2 minus A minus B, B A minus lambda 1 times 1 over B times lambda 2 minus lambda 1. Okay. Yeah. So that's 24, where I don't like this yeah, so what happens when B is equal to 0, for example?
And then you get 1 over 0.
No, so then basically what will happen is that you realize that this B cancels out these B's, right?
Yeah.
Okay, if I bring the B inside over here, it cancels out these. If I bring the B over here, because you will find that it also comes out to something else. Alright, so it will be a limiting case. You have to deal with that specially.
Okay.
So if I had, for example, used the other equation, then I wouldn't have got this. I'd probably have got C or something like that. Okay, so this is this is an equation that is only valid for if B is not equal to 0. So let me write this down. Okay.
Yeah.
This is valid only if B is not equal to 0. But if it is, just use compute lambda 2 minus A over B minus 1 plus 1 A minus lambda 1 over B, okay, which is basically this P inverse.
Yeah.
P inverse, right? As B tends to 0, okay, and it will let's write this properly. And it will be well defined.
How does that ensure that it's going to be well defined?
So there is just one slight case where it won't be well defined. Okay, but for most cases it will be well defined, because what's going to happen is what you're going to do is if you substitute the actual value of lambda 2 minus A over here.
And that depends on.
Yeah, and so let's go back and see. Where is it?
Depends on B, right?
Yeah, it depends on B. And so there'll be a B there which will cancel out.
Cancel out.
Yeah.
The limit will.
Yeah, in the limit. And except that even this has one caveat.
Okay.
There are situations, I'll show you an example in a second, where you can't eigendecompose. Remember that I mentioned that in class and I said we're not going to worry about it. I'll show you an example where that happens later. So basically that happens. So we have, where is our P? We got our P to be this quantity out here, right?
Yeah.
Normally, for almost all situations, lambda 1 minus a is not equal to lambda 2 minus a. But for certain matrices, this can happen.
Okay.
That lambda 1 minus a is equal to lambda 2 minus a. For example, if lambda 1 is equal to lambda 2.
Right.
Okay?
Yeah.
When that happens, this matrix is not invertible.
Right.
And that's when this whole thing breaks down.
Okay. Okay. Then you can't have that.
Because then I can't. That's the situation where it breaks down. But there, basically, you can put it in a slightly different form called Jordan canonical form.
Oh.
So the whole thing is, so you'll have a different P in general, not this one. Okay, and you'll have a 1 out here.
Where?
Here.
Oh,
the lambda is no longer diagonal.
Oh.
It'll be there'll be ones on the immediate higher diagonal.
Oh, okay.
Okay. Some ones on the immediate higher diagonal. So that becomes complicated.
Yeah.
Okay. So this is the well defined, and the star if lambda 1 is not equal to lambda 2. If it then if lambda 1 is equal to lambda 2, okay, then eigendecomposition not possible. Not possible. Have to use Jordan canonical form.
Can we turn up the light?
Sure. If you could just go there and turn that light on over there. Oh, right. Yeah, and actually there are more lights. You just twist that little knob. You turn it up as much as you like. Yeah.
Thank you.
Yeah, then we'll have to use Jordan canonical form. Okay, so this 2x2 example gives you a lot of insight into the general case for the n by n. All right. If so here we know that it's going to be all right. Well, we still haven't proven that this limit is going to be okay, but we can do that right now. Okay. But we realize that if the two lambdas are the same, then there can be a problem. Okay. The same is true for bigger matrices. If many lambdas are the same, or at least two of them are the same, then there can be a problem. Here there is a problem. There might be a problem. Okay.
Depending on the position.
Depending on the positions, exactly. Yeah. So the moment this P matrix starts becoming, rank deficient, that's where the problem is. And it can become in bigger matrices rank deficient in many different ways.
Okay.
Many combinations can.
Right.
So that is why but the Jordan canonical form still holds over there. So that's the, that's the whole picture.
Okay.
Of the thing. So let me, the only part of the picture that we haven't actually really worked through is where are lambda 1 and lambda 2? Somehow I seem to be missing it all the time. Here it is. Here. I will put a box around it. Green box. Okay. So here's so there's B as the only place where B is. All right. So lambda. So I think it was lambda 1 minus A and lambda 2 minus A or something like that. Okay. So if you take out A, then it's just D over here. What is the limit going to be? We probably have to use L'Hopital's rule. No. But if I take lambda 1 minus A, then this becomes minus A, D minus A, because there's a divided by 2 out here.
Right.
Okay. So it becomes D minus A rather than A plus D. And if I use L'Hopital's rule,
you take the derivatives, right?
Yeah, I have to take the derivatives with respect to B. Okay. and if I do that, then these go away anyway.
Yeah.
Okay.
The a plus d terms go, right?
Yeah, the a plus d terms go. This square root becomes a 1 over square root, 1 over 2 times square root or whatever. Okay, and then I have the top is just going to get a minus plus 4 times c, I think.
Yeah.
Plus 4 times c. Okay, and then we have to figure out. So if c is 0 in that, then it's going to be 4ad out minus 4ad in the denominator. This is going to have a 2ad term.
Yeah.
Okay, so it's going to be actually a minus d squared, because if this is this a plus d squared will give you a square plus d square plus 2ad.
Yeah.
Then minus 4ad is going to give you
Minus
so it's going to be a minus d squared.
Right.
Okay, and a minus d squared is going to now become root of that is just a minus d. Okay.
Yeah.
And it's well defined, provided like d minus, and this was also a minus d over here, or minus a minus d or something like that.
Yeah.
Okay, so and then one of them actually can become 0. Can it? Well, there was a c2. No, that was we have to work it out.
Yeah, we're trying to find the derivative, right?
Yeah, that was the derivative, and that well, actually, we're trying to find the limit of this expression as b goes to 0.
But we want to use L'Hopital's, so.
Yeah, well, so as if I divide this by, I have to divide this by b, right?
Yeah. We have to subtract it. We're trying to find the limit.
Yeah, so actually,
a,
no, so it won't. I don't have to. I got confused there. I don't have to subtract it from that. We are just going to get a minus d squared divided by 2 or something like that. Okay, that's it.
Okay.
And a minus d squared divided by 2 is perfectly well defined.
Yeah.
Okay, this b is 0. So that's going to work out.
Yeah.
All right. Having done that, now we can actually I want to box this here. Okay. So 24 is the key equation that we are now going to be relying upon. Okay. So now we return to.
We did this for the general 2x2.
We did this for the general 2x2. So life is very good for any 2x2 example from now on. Okay. So let's return to the specific A for our RLC circuit. Okay. A for our RLC circuit. Okay, I'll do this on another. Well, actually, there's plenty of space. So what was that A? Yeah, 6, which is in 6.
Yeah.
Right. So this is. Right? A is equal to this, which means that small a is equal to 0, small b is equal to 1, so we won't run into that problem here anyway. Small c is equal to 1 over L equals minus 1 over LC, minus 1 over LC, and small d is equal to minus r over L. Okay, so let's see what happens here. Let's also lambda 1 comma 2 equals what was it now? Here we go. Equals equals a plus d. What is a plus d? It's minus r over l, right? Minus r over l plus minus,
over L.
I'll put the 2 over here because I don't want to have to divide it. So plus minus half square root of a plus d whole squared. A plus d whole squared is r squared over l squared, right?
Yep.
R squared over l squared minus 4.
Times
A times d is 0, mercifully,
LC.
and
1 over LC.
and minus bc. B times c is okay, so there's a plus and a minus, this thing going on here. Minus 4 times, let's see, AD is 0, and it's going to be, and what is bc? B times c is minus LC, and there's a minus here,
So
so it's going to be plus LC.
1 over LC.
Yeah, 1 over LC, right? Plus 1 over LC, 4 over LC, and there was a minus outside anyway.
Yeah.
Okay, one has to be careful about these things. Okay, so it's not too bad. Okay, minus 4 over LC. Let's double check this because everything depends on it. You got the same thing?
Yeah.
Alright, fine. That's good.
Yeah.
Okay. Right, so this is going to be our equation number 25. And now let's find. Okay, we actually have. I'm not going to be substituting the lambda 1 and lambda 2, but we can at least substitute the a, b, c's, and d's, which are relatively easier.
Yeah.
Okay.
Yeah.
So now we can. That was 24. Equation 24 becomes. And 24 becomes what was our a here? Yeah. A equals this, equals. All right. What were our various numbers? Here we are.
We just need A and B.
We just need A and B? We don't need C and D? Oh yeah, because we didn't use that second equation in order to, yeah. C and D are somehow encapsulated inside the lambdas.
Yeah.
Okay. And what were A and B, by the way? 0 and 1.
So it's simple.
Yeah, okay, that's very good. Yeah. So A equals 0, B equals 1, right? So what we get is 1 lambda 1 lambda 2, right?
Yeah.
And then we get lambda 1 lambda 2, and then we get
Lambda 2
lambda 2 minus 1
minus lambda 2
minus lambda 1, I think.
Lambda 1, yes.
Yeah, minus lambda 1, and then what will be again 1, right? And then we mustn't forget the determinant. That was lambda 2 minus lambda 1.
Yep.
Right. Okay, splendid. So you got this. And this should be number 26. This is also worthy of boxing. Alright, so let me also. So P lambda P inverse, right? Okay, so we've got that. Now how to use it?
Yeah.
That is the question, right? How to use it? Well, let's see. I think we had a number 2. What was number 2? yeah, okay, that was the aside. 2.1. Okay, so now it's 2.2. We are going to solve 6. Okay.
Oh, yeah, state equation. Right?
Yeah. So 2.2. Now we can return to solving 6. Now it gets a little bit easier. Solving 6, which we can repeat here. This was A, right? So now what we're going to do is we're going to, and this is x over here, and this is x again, right? So we have, this is dx by dt. Let's go back to black. Dx by dt equals ax, right? That is equal to p lambda p inverse x, right? And now, so let me write it again. Dx by dt equals this. And now what I can do is I can pre-multiplying by, so multiplying by p inverse, I get d by dt of p inverse x. I move the p inverse inside, equals lambda times p inverse x, right? This is the whole game of eigendecomposition, right? And then I define y is p inverse x, right? And that is the same thing we need to as x equals py. So yeah, so that I should give this one especially a number 27. Right. Okay, so then we have dy by dt equals lambda y, right? And that also I should give a number 28, which we can now expand.
Yeah.
That implies dy1 of t by dt equals lambda 1 y1 of t, right? This will be 29.1, and dy2 by dt equals lambda 2 y2 of t, and that will be 29.2. And the whole thing is called 29. Oh, have I done?
Oh, these are just first order.
And these are just first order, so we're going to, and they don't even have any inputs, which makes life very convenient actually, because otherwise we'd have got that convolution integral, which we'd have had to worry about. Okay, that's what happens in the recent lectures. Okay. Yeah. But without an input, it's really easy because it all depends on an initial condition.
Yeah.
Okay. So okay, this too may be worthy of boxing. Okay, solution to 29. Solution to 29. Let me see. It's y1. You can just write it off. y1 of t is equal to y1 of 0, which is the initial condition,
Yeah.
times e to the power of lambda 1t, right?
Yep.
Lambda 1t, y2 of t is the same thing, because y2 of 0, e to the power of lambda 2t. And this 2 is a very nice set of equations, so we can 30.1 and 30.2, and together it's 30. Okay,
Yeah.
and we can box this too. So, having got this, now the one question is, how do you get y? We might know the original system was given to us in x,
Yeah.
right? But this solution is in y. How do we know the initial condition? We need the
In
initial.
X.
Hmm?
We know it.
We know in x.
Yeah.
So we have to from x we have to get the initial condition in y. How do we do that?
Using the definition. that
Using the
we gave for
definition of y precisely.
Yeah.
This definition number 27 over here.
Yeah.
Okay, so y0 in particular is equal to p inverse x0.
Yeah.
Okay, so the initial conditions, the ICs y1 0 and y2 0 are given by 27, which is to say y1 0 y2 0 equals p inverse, I think it was, right?
P inverse.
x1 0 x2 0. So there's no hassle there. And this is 31. Right? And since we actually have an expression for p inverse, we may as well apply it right now. So hopefully it won't be too messy. Actually, it doesn't look that bad.
Yeah.
Equals this times x1 0 0 x2 0, right?
Yeah.
Okay, now can we simplify this a little? So we'll put the 1 over lambda 2 minus lambda 1 in the beginning.
Right.
And then it's lambda 2 x1 0 minus x2 0, lambda 2 x1 of 0 minus x2 of 0, and this is minus lambda 1 x1 of 0 plus x2 of 0, right? Yeah, bad enough, although I suppose it could have been worse. Okay, but it is completely general. I can give you any initial condition on your capacitor and your inductor and you will get it.
Yeah.
So soon what we'll do is we will probably make, so x2, if I remember, what was x2? Right? It was dVc by dt, right?
Yeah.
Right? And dVc by dt was basically the current.
Right.
Yeah.
Yeah.
Yeah, basically.
Kind of
Yeah.
oversee, yeah.
Yeah. So we'll make that 0,
Okay.
and then this will make life a little bit easier. Okay. So if x2 is going to be 0, yeah, it's just going to be this first term. Okay, but we'll leave it as it is for the moment. So we'll do all those things right at the end. Okay. So that's how it is. So so then let's let's go to the trouble of actually writing out these in terms of this. So that is to say, so 30 becomes y1t y2t You see why Michelle didn't go through this in the class.
Yeah.
But it might have been helpful to have a video or a document up on the side. Okay, y1 0. So equals 1 over lambda 2 minus lambda 1. Just this first thing over here. Right, and this times this whole thing times e to the power of lambda 1t, right? And the second thing over here times e to the power of lambda 2t. Okay, right, so and this can be 33. So at least as far as the y's are concerned, we've got actually an equation for everything. Okay, now the last step is to apply p to y to get x. Okay, so we'll just have to do one more matrix multiplication, and then we are finally done. And let us hope that that matrix is not too bad.
It's not.
It's actually not that bad.
1 1.
It's 1 1 lambda 1 and lambda 2. And mind you, in the case when the thing is complex, lambda 1 and lambda 2 are obviously going to be complex conjugates of each other.
Yeah.
Okay. So then eventually what we'll have to do is we'll worry about that case. We'll turn lambda 1 and lambda 2 into some a plus ib, or alpha plus I beta, and alpha minus I beta. Okay, and then we will see what happens to all of these. Okay, that's really the final step here. And this lambda 2 minus lambda 1 will always be real,
right? Because
it's the imaginary parts that have opposite signs. Okay, so we'll have to get to all that, but one step at a time. Okay, finally we want to express x of t from y of t using I think it was 27 if I'm not mistaken. 27 indeed. Using 27. Okay, x of t equals p times y of t. Okay, which is to say x1t x2t equals, here is p times I'll take this 1 over lambda 2 minus lambda 1 over here, 1 over lambda 2 minus lambda 1 is here, and then this whole quantity here. Oh, a lot of space. Alright, and let's try to write it out without making too many mistakes. Lambda 2 minus lambda 1. Okay, so 1 1 means just add these two, right?
Yeah.
So it's going to be, I'll just copy and paste here. This, we should squeeze it a little bit. Plus this. The second one is basically you have to multiply the first by lambda and the second by lambda 1 and the second by lambda 2 and add them. Yeah, so it's getting worse. But still, I mean, it could be even worse, and so one should give thanks for small mercies. Second one is lambda 1 times this plus lambda 2 times that. Alright, so finally we have it. Now we just have to write x1 x1t x2t is equal to this, right? And this is a wonderful equation, so it can be boxed. 34. I just hope that we haven't made any mistakes.
That's the unfortunate.
Yeah, well then one has to go back through the whole thing and correct it,
Yeah.
which is going to be a real pain. Okay, 34. So finally, so this is the solution of your equation system.
Mm-hmm.
All right. Now let's take a look back at that document and see whether anything looks similar. Okay. This is a solution for anything, whether lambda 1 is real or whatever it is. Okay. We just have to look at the complex case and simplify it a little bit.
Yeah.
Okay. Just make sure that this j doesn't arise.
Yeah.
Okay. I mean, is there any implication over here that this k1 minus k2, or maybe this is correct, this k1 minus k2 actually, if this is imaginary, then it might be all right. Have they said anything about it?
No.
Ah,
Yeah.
that's not very insightful, although it may actually be correct.
Yeah.
Yeah.
They kind of just went from that to this graph, which is like that.
All right, we'll get to this graph too. It's all a question of time and effort. All right. So we are particularly interested in the case. Yeah. Okay. When the underdamped case, is when lambda 1, lambda 2 are complex. Okay.
Right.
That is to say, non-trivially complex, have non-zero, any number is complex, imaginary parts, right? So first observation, if lambda 1 is complex, then lambda 2 is equal to lambda 1 conjugate. Okay.
Right.
Second observation, if lambda 1 is complex, then p1 is equal to p2 conjugate, simply because we have that.
Yeah. Yeah.
Okay. Second observation, if lambda 1 is complex, then p1 is equal to p2 conjugate, right? So we're going to write out everything in terms of this. Okay. So actually, how do we know this? We check. What was the number of that? 12.5 was it?
Which one?
Actually, I think it was 12. The equation 12, where we actually had expressions for the lambdas. Just check 12. Okay. Check 12, and where was the definition of P1? Well, we had a P1 defined somewhere. Oh well, whatever. I am not going to write it. People can figure it out on their own. Okay, 14.
Yeah.
Okay, check 14. Right. Right. So define lambda 1 is equal to see which are the alpha plus j beta. These guys also have a beta, right? It can get royally confusing. The alpha is fine. Should I call it omega?
I mean, it would be the same thing.
Let's call it beta. I'm not sure whether that omega is the same as this. Okay. Then, this is an important definition. So that's 35. Then lambda 2 is equal to alpha minus j beta. Okay, and p1, well, the whole of p is actually equal to, I think it was 1 1 lambda 2, right?
Yeah.
Equals alpha plus j beta and alpha minus j beta. Okay, and what is p inverse? Okay, so lambda is equal to alpha plus j beta 0 0 alpha minus j beta. Okay, and what is p inverse? What is p inverse?
One over b.
We might not actually need all this. So, all right, we'll just leave it at that because we already have the whole thing worked out.
Yeah. We got the solution right here.
We have the solution right there. So all we have to do is go through the incredible pain of. All right, then we want lambda 2 minus lambda 1 for a start, right? So, we won't number these. So lambda 2 minus lambda 1 becomes equal to minus 2 j beta.
Yeah.
Okay, that's 36. E to the power of lambda 1 t. Okay, e to the power of lambda 1 t becomes equal to e to the power of alpha t times e to the power of j beta t. E to the power of lambda 2t is almost the same thing, e to the power of alpha t, e to the power of minus j beta t, right? Lambda 2 x10 minus, so I think the time has come for us to start separating. So this whole thing is imaginary over here, okay? For the whole thing to be real, this whole thing has to be imaginary. Okay, so let's find out whether it actually is or not. Can we simplify this a little bit? Yeah, let's try to do this. Okay, so x1 minus x2 becomes, so this whole thing becomes lambda 2 was alpha minus j beta, right, times x1 0 minus x2 0, the whole thing in square brackets, e to the power of alpha t, e to the power of j beta t plus minus lambda 1, which is to say minus alpha minus j beta x1 0. We're going to collect the x10 terms together, okay, and the x20 terms together afterwards. X10 times what is it? Plus x20, right?
Yeah.
Close square brackets. E to the power of alpha t, right? E to the power of minus j beta t, because that's alpha 2, right?
Yeah.
So this is equal to that. Let's collect the terms of x10 together. That's going to be, so that's going to be alpha minus j beta over here, right, times e to the power of alpha t. Actually, e to the power of alpha t is completely common, so we'll take it out altogether. E to the power of alpha t, right, this goes completely outside.
Yeah.
And then we have e to the power of j beta t over here, right, and then we have minus alpha plus j beta, okay, right?
Yeah.
So the complex conjugate of that, but with a minus, right, times e to the power of minus j beta t. You observe something nice about this?
Complex conjugate.
These two are complex conjugates and they're subtracted, therefore this, the whole thing is imaginary.
Okay.
Okay, and it's nice because it's imaginary, because we had this lambda 1 minus lambda 2, or lambda 2 minus lambda 2 to be this, and that's going to be multiplying this.
Okay, so then the J's terms.
So then the j terms cancel out and
Yeah.
we get something real.
Real, okay.
Everything multiplying x naught, x1 naught is going to be real.
Mm-hmm.
Okay,
Yeah.
that's what's going to happen. Okay, so and the x2 thing will be similar, but let's write it out. Okay, where's x2? So x2, it's minus e to the power of j beta t, correct?
Yeah.
Plus e to the power of j beta t, isn't it?
Plus e to the yeah.
Plus e to the power of minus
Minus
j beta t, which is again the same thing.
Yeah.
These two are complex conjugate of each other and they are subtracting. So this is also going to be imaginary,
And then we're multiplying that with
and multiplying that with an imaginary number will lead to a real thing. It had better be.
Yeah.
Okay, so that's basically what it's going to be. So let's now let me actually now what I'm going to do is I'm just going to say 1 over lambda 2 minus lambda 1 of this equals 1 over lambda 2 minus lambda 1 of this whole thing. Okay, equals, let's just move this a little bit. Yeah, e to the power of alpha t over lambda 2 minus lambda 1. Okay, and that is equal to what was that? Minus j2 beta equals and minus j2 beta is, I can, if I divide it by minus j2 beta, the minus j becomes a plus j.
Yeah.
So it becomes j e to the power of alpha t over 2 beta, right?
Mm-hmm.
Times this whole thing over here, which you can try to write in one line. This plus that. Something to the left. And well, okay, we've actually forgotten. So this is, have we left anything out of the, that is actually x1 of t.
Yeah.
Right?
Yeah.
So that's x1 of t. So I'll just squeeze this a little bit and I'll write x1 of t. Implies x1 of t equals this wonderful expression. We'll get to the sines and causes in 1 second after this. Actually, let's just deal with x1 of t and then we'll worry about x2 of t. It is tempting to actually complete the whole thing, painful though it is.
Mm-hmm.
Okay. So, alright. So that's 37. So now let's see. If I, right, so what we're going to do is save ourselves a little bit of hassle by saying that, okay, call this, give it some name, z, okay, and then this is z bar,
Yeah.
okay, and this is, what do we call this, x, no we can't call it x, w, and this is w bar, right?
Yeah.
So without the minus, actually, that's important. Right, that's w, and this is w bar, or we'll call this w bar and we'll call this w.
Okay.
Okay, so so we have minus, and we have
Negative.
let's call this w and call that w bar and put a minus out here.
Yeah.
Okay, right? So that equals it's going to be 2 times the imaginary component of c, right? J e to the power of alpha t over 2 beta times 2 times imaginary component of c. Am I right?
Yeah. Because the alphas go.
The alphas will go away, but imaginaries will be minus or plus. I think it will be plus 2 times. imaginary component of z, right? Let's see.
It's like minus j beta e to the jb beta
Yeah.
t. Then you have minus.
No,
So-
no, I'm not even looking at this whole thing.
Oh, okay.
I just say that z is equal to some z1 zr plus jzi.
Yeah.
Okay, then z bar is equal to zr minus j zi, right?
Okay. Yeah,
Subtract the
that's
two
what
together,
we-
you get 2j. Yeah, so this is correct.
Yeah.
Okay. The other one will be minus 2 times. Okay, times x10 plus, this is w. Okay, but it is no, it's not w minus w bar, it's minus w plus w bar. Okay, right, and this is, I think, going to be minus 2 times. This is minus 2 times imaginary component of w times x10. Sorry, that's going to be an x20. I made a mistake. I'm pretty sure of that.
Yeah, it'll be minus 2.
Oh, and I wiped this out.
You cut it instead of copy.
I cut it instead of copying it. Great. All right, I'll just remove this. And that was it, was it?
Minus 2.
Imaginary component times x2 of 0.
It's 2.
x2 of 0.
Mm-hmm.
That was pretty much it, right?
Yeah.
And so let's find out what is the imaginary component of z?
Beta.
Imaginary component of alpha. Oh, I think it's going to be worse than this, just that. Okay, so imaginary component of j beta t, right? And that is equal to here's where the sines and cos come in. Alpha minus j beta imaginary component. Alpha minus j beta times cos beta t
Minus j.
plus j beta sine beta t. Okay. Now we care only about the imaginary component. So that is going to be, let's see, so minus j beta, so minus j beta cos beta t, right?
Yeah.
Plus j alpha sine beta t, right? That's what it is.
Yeah.
Okay. And so that's what that's going to be. And what is the imaginary component of w? That's actually much easier. So the imaginary component of w is just the imaginary component of e to the power of j beta t, because that was w.
Yeah, yeah.
Okay, and that is equal to just j sine beta t.
Right.
Okay, so now we can plug these two things in. 38, and we should have given this a name. Actually, it should be now 39. This is 38. Okay. Right, 38. So putting x of t using 38, using 38 and 39, we have x1 of t equals, okay, j alpha t over 2 beta. J alpha what? J e to the power of alpha t. E to the power of alpha t over 2 beta times 2 times, yeah, we will pull the j out over here, and we'll also put the 2 out over here.
Yeah.
Okay, and 2 times that quantity which is beta cos beta t plus actually minus. There's a minus there. Be very careful about things like that. So alpha sine beta t, right? That's correct, right?
Yeah,
looks roughly correct.
Yeah.
See, this 2 and that 2 is going to cancel out later. That j and that j is going to going to become a minus.
One.
And this was times x1, right?
Yeah.
0. And then the other one was probably much simpler.
Yeah.
J times 2 times sine beta t times x2 of 0. Okay, you're almost there. Okay, and that is equal to, finally, the j and 2 will get rid of it. All right, so it's just e to the power of alpha t over beta.
Yeah.
And then we have to, the two j's become minuses. Okay, so then this becomes beta cos beta of t minus alpha sine beta of t, right? And the whole thing times x1 of 0, and this is going to be a minus
2.
the 2 goes away.
All right.
Yeah,
So
sine beta of t, beta times t, x2 0. Yes, finally.
there's no imaginary.
There's no imaginary, of course not.
That makes sense.
Yeah,
Just purely because it's all complex conjugates.
because everything comes in complex conjugates, has to be.
Yeah. That's cool.
All right, it's unfortunate that it has to take such a long time and so many details to actually see this for real,
Yeah.
but well, that's how it is.
Awesome.
Okay, but we still haven't finished. Do you want
Yeah.
to finish the rest yourself? Or
I think I see it now. Yeah.
yeah, but maybe I should just finish it.
Okay. Yeah.
Okay.
If we started, we can go.
Yeah, maybe in 20 minutes it'll get finished.
Yeah.
How long has it been? 2 hours.
Yeah.
I thought this would take half an hour. Okay, so that was x1 of t. Okay, we should put a big box around it. We should put a big box around it. And in fact, even change its color. I don't know, now I've forgotten what beta was.
Beta is
yeah, well, it was whatever the complex part of that was. Yeah, I remember now. So for example, if you said r is equal to 0, then beta is equal to omega naught.
okay. The natural.
The natural frequency. J omega naught. I mean, actually, just omega naught.
Yeah.
The J is taken out.
There's no loss.
Yeah. Okay, so then, but here's the interesting thing. So if beta, if r is not equal to 0, okay, then the imaginary part is not omega naught. It's omega naught plus some square root of omega naught square plus something to do with r over L. We can take a look at it right now.
Like minus.
So this is one big piece of insight, which is not that I don't think it was stressed. Yeah, it was this, right? You can take the 4 out and get rid of this 2.
Yeah.
Okay, and so then it will be basically this r square over it will be r square over 4L squared over here minus omega naught square.
Yeah.
And so it'll corrupt the omega naught square a little bit over here. Okay, so the frequency of oscillation, which is basically this beta.
Yeah.
Okay, because it goes inside this inside the causes and sines.
Yeah.
Okay, that changes a little bit.
Yeah.
And I dare say that depending on which, so the other thing that I wanted to do was to connect this with the phasors, with the body plots and all that, because it's all the same thing. Okay. But you'll see also that the peak shifts a little bit depending on what output you're taking.
Okay.
Okay, if the peak is not always at omega naught.
Okay. Yeah.
Yeah. Of the body plot. Yeah. Okay, so. Yeah, the fact that we haven't got it to be imaginary is very nice, because it means that the chances of having made a mistake are somewhat lower. Okay, so now we go to, now let's solve for now we solve for x2.
It's just the derivative of that. Just wait.
It's the derivative of that, is it?
Yeah.
Oh yeah. That makes it much easier.
Yeah.
We don't have to actually use that formula.
Yeah.
Okay, that's splendid. Okay. let me just make a note that you could use that formula. You could use 34, but it's better you could use 34, but it may be easier to use the basic definition. X2 is equal to dx1 by dt. Okay. And so that becomes very easy then. dx1 by dt equal, though there are two it's not that, it's not that hard. It's alpha over beta e to the power of alpha t times this whole quantity, right? Chain rule and all that, plus e to the power, we'll have to simplify it a little bit, plus 1 over e to the power of alpha t over beta. Beta minus beta squared sine beta t plus alpha beta cosine of beta t, right?
Yep.
x1 of 0. Next one hopefully will be a little bit better. Minus beta cosine of beta t x2 of 0. Okay, so actually the several betas cancel out in the second one.
Yeah, when you
so let's see, do any betas cancel out here? No, they don't. So we can take out, oh great, this is just god awful. Well, we want to keep it in x1 terms and x2 terms.
Yeah.
So e to the power of alpha t is for sure. Okay.
You just take the beta inside.
Yeah, I'll take the beta inside and also the alpha inside. There's an alpha.
Oh, right.
Yeah. E to the power of alpha t is there. All right. Now what are the
Negative alpha.
So this one over here, this is the x1 term,
Yeah.
right?
Uh-huh.
So this becomes alpha cos beta t, right? Because the beta and beta cancel out. This alpha hits this beta and beta cancel out.
Yeah.
Okay.
Yeah. Mm-hmm.
And then this becomes minus alpha squared over beta sine beta t.
Yeah.
Okay. Now we have to get this other part out here. Minus beta and beta cancel, beta square cancel out to make beta.
Okay.
Beta sine beta t plus alpha cos beta t, and this whole thing is times x10. Now before we even go on further, does anything cancel out? No, nothing cancel out. This is the
These combined.
These combine, but they become just 2 alpha
Yeah.
times this, and well, too bad. Yeah. Okay, plus. Okay, then we have to deal with these other terms over here.
Minus
Alpha over beta, right? Minus alpha over beta sine beta t.
Minus cosine beta t.
Minus cosine beta t. So we can put the minus here. Cosine beta t, right?
Yeah.
Times x2 0. Can this really be correct? What a terrible expression.
No imaginary terms, so.
Well, no imaginary terms, but still one would have hoped that there would be a slightly better, more symmetric sort of thing about it, but alas, no. Unless there's a mistake.
Yeah, but I guess the most simplification you do is just like group the signs.
Yeah, we can just. Oh, okay. Well, maybe we can do that. Or does it help if I group the signs and factor it, and the cosines and factor it?
Well, these just combined will be 2 alpha.
There will be 2 alpha cosine, and then it will be that 2 will go to the 2x1, right?
Yeah.
2x1 plus x2 minus x2, because there's a cosine here too.
Yeah.
Okay. and the signs will have
minus alpha squared over
beta minus alpha over beta. Maybe one can do something with that. That's not a very
You can.
so, we'll just leave it like this. Okay. So what in that document, there is no clarification on what k becomes, right?
They
K1,
just say,
K1
like,
and
use
K.
the initial conditions and this.
Yeah, well, okay, but I mean that hasn't been worked out. Well, now you can see why.
Yeah.
So if you use the initial condition, because these really god awful. Okay, well, let's write it in terms of these things anyway. Okay, so then that is equal to
Like grouping the terms.
yeah, I'm grouping them. So it's 2 alpha cosine beta of sorry, no, the cosine is outside. 2 alpha x1 of 0, right? 2 alpha x1 of 0 minus 1 minus x2 of 0, okay, times cosine beta t, and the other one is everything is a minus, I think.
Yeah, we can
all
do
of them are minus. Yeah,
minus, yeah.
so minus alpha square over beta minus beta.
No,
Okay,
plus
what is
beta.
alpha square?
Plus beta.
Plus beta. Alpha square over beta plus beta. Isn't that just alpha square plus beta square over beta? Yeah, I think so.
Yeah.
So alpha square, that looks nicer than this. Okay.
Okay, then minus alpha.
Yeah, times x1 0. There was
There's
a
minus alpha from here.
yeah. Yeah. There's a minus 1 from there. No.
No,
we
no,
need
because the x2,
we need the
yeah,
x1 0 here. Okay. And then it is, what's the other one?
Minus x2 times alpha.
Minus no, that's also a minus.
Plus,
That's a plus.
Yeah,
Okay.
plus x2.
Plus
Plus
1
zero.
over alpha over beta, right? Alpha over beta x2.
Yeah, and then we can just. Well, I was just putting it under the common denominator.
Yeah. That's right. Yeah, we can. So this, we can just put the common denominator out here, or we can even put the common denominator over here, right? Is that correct now?
Yeah, no, it's
I
correct.
missed a. Okay, that's times sine beta of t. All right, that's what we actually wanted. We didn't do this one in that form, but it can be left as an exercise, I guess. So, and this is like 41.
Yeah.
That's x2 of t. Okay, are we done?
Looks like it.
Okay, fine. How long does that take?
Recording.
It took less than I expected, 20 minutes.